Hello everyone, welcome back to my channel. Today we're going to talk about another dynamic programming pattern, the 01 knapsack pattern. This is another really interesting one actually. So let's say 01 knapsack. Zero one there means, like binary, 01, false and true, true and false. Yeah, and then what this means, it translates into code. So it's exactly the same thing. It translates into code into, imagine, like take or not take. Yeah, skip or you take, like two choices. So like inside the implementation, what we have is a decision tree whereby for at every point we need to make a decision whether to take a value or not take a value. Yeah, so remember our the question that related to finding the sum of the elements in an array when you cannot pick adjacent values. So the question was something like you had a pattern of three, let's say four, and maybe we had two, we had one, then there is let's say three, and then there is nine, there is then four, and then there is 11. Yeah, so let me make it a little bit more interesting. Let's see that we have okay, let's have zero here, and then let this one be let this one be one, and then this one be five. Yes, so let's do like this. Okay, so this kind of depicts well. So naively, if you want to solve this problem, you probably say, okay, I mean, we want the sum of the numbers here whereby we cannot pick adjacent numbers. So what that means is that if we pick 5, we cannot pick 1. Like if you pick 5, we should jump to 0, like that. So naively, what we think is, simple ways to solve it is to say, okay, let's just pick values at the even indexes. Yeah, so indexes, start from 0 in programming languages. So we'll say that all the even indexes are the ones we pick. So we'll pick 5, we'll pick 0, we'll pick 5, we'll pick 0, we'll pick 2, we'll pick this one, we'll pick this one. So the sum of all of this is 5, 7, 10, 14. So that's 14. Yeah, and then the other option is maybe let's try the odd indices. So if we try the odd indices, see which one is higher. So we'll pick 1, pick 4, pick 1, pick 9, pick this one. So what do we have? We have this is 5, 1 plus 4, 5 plus 1, 6. This is 15, and that's 27. Yeah, but none of this is actually the answer. Yeah, there's a better solution here. So I'll show you. So what if we picked 5 and then we picked 4? Then we pick 1, then 9, then 11. So I mean, first of all, is this valid? Think about it. So we want values from this array, but then we just want to make sure that those values are not close to themselves. They are not immediately adjacent. So we can pick 5 and then jump to 4. We don't have to pick 0. First of all, we cannot pick 1, but we don't have to pick 0. We can jump to a value that is better if we feel like it's a better value. Then we have to pick 2, but then we can pick this guy 1, or we pick 3. Yeah, but the problem in picking 3 is that we'll not be able to pick 9. That's the problem. So rather we'll just somehow realize that, okay, let's pick 1. Then when we pick 1, we pick 9, and then when we pick 9, we pick 11. So is this a higher value? Let's see. Let's first be sure that we've not said something wrong. So 5 plus 4, 9, plus 1, 10. 10 plus 9, 19. 19 plus 11, 30. So you can see that's a better value. That means that the solution to picking a better value doesn't mean that we need to immediately, skip to the next one. Oh, sorry, skip the next one and then go all the way to the next. Right? We are not sure. We are not sure what we need to skip, but there is a combination. There's a way to skip. So this is the kind of questions where 01 Knapsack actually shines. So the idea is just, imagining that we can do a kind of brute force at every point, decide on whether we want to take or not take. So that's where the 01 Knapsack idea comes up. So we have an index. We will go through all of the indices one by one. For every index, we decide, do we want to pick 5 or do we not want to pick this value at this index? So at every point, we have like two choices. Do we want to take 5 or we don't take 5? Yeah. So the issue now is that once we take 5, we need to skip the value at this index and then jump onto the next one. That's the point. So at this point now, here was the decision to whether take 5 or not. If we have taken 5, and here is the design decision for the next index, which is whether to take 1 or not, we cannot take 1. Yeah, so this is going to be an invalid part. We need to not take 1. So once we are done with that, next thing is we evaluate the next value down the trees. Yeah, so what will be the value for the level for 0? So you imagine that this is a level for 1. For all of the indexes, we will evaluate them that way. So this will now be the value for 0. We now need to decide, should we take 0 or not? So we can decide to take 0 or we can decide to skip 0. So you can see, if we take 0, then we can no longer take the value at the next index, which is 4. We need to skip it. Yeah, so this step here will be evaluated to 4. We need to skip this 4, and then this other point here will be sorry, this is the point where we take 4. We need to this will be invalid. We need to skip it. This is the value where we do not take 4. Yeah, and then for this other point, this is where we take 4. We can take 4, or we can even choose to not take 4. Yeah, and then if you kind of follow this tree, you realize that this part here, this part here, this one here is the one that leads to our solution. So we need to keep drawing. The tree doesn't end. Actually, it hasn't ended yet. The tree still continues to grow because we have not finished. I'm only at the fourth index 3. Yeah, but this is the part that gives us the answer. So imagine that we'll now draw everything all the way down to the base part, and then we'll now sum all of them together to now find, we'll sum the values, the sum at each of the bottom parts, right, to figure out the solution. So for example, now at this part here, the sum here is right now is 9. Yeah, but we're not done evaluating. We need to continue exploring everything. For here, the sum here is at this point here is 5. This is 5. We did not take 1. We took 0. So this is 5. This is an invalid part. We are not going to explore it anymore. Yeah, but basically you can imagine that the total number of parts, at every point we are splitting the part into 2. So that means that the total number of leaves that we'll get at the end of this tree will be 2 raised to power n, where n is the size of this input array. So because we are splitting, we have a decision of whether take or not take. Yeah, so that is 01 Knapsack, and that's the approach to solving this problem. Yeah, but however, we can do this with the same approach that we discussed about for Fibonacci. Yeah, we can use recursion to solve this problem. We could use push, pull, DP, whichever one it makes more sense. So usually at the end of the day, there's going to be one of those approaches that is easier for you to solve. For most people, it is the recursive approach, usually the easiest way to solve for most people. Yeah, but if that is not always true. For most people, that is the case, but at the end of the day, it's not always true. Yeah, but basically that's it. So let's now try to solve this using recursion. So what we'll do is that imagine that we want to solve for let's say we want to solve for So we have the entire input array. We'll have a function. Let's say our function is called dp. The function is going to take the index that we are in. Remember, the index I is what determines how we move. Then the function also takes in the array. So what does the function do? So ideally, what we want to do in the function is we either choose to take a value at an index, yeah, or we do not take. So in which case we say we skip. Remember, this is 0 1 knapsack, take or not take. So when we are taking a value, what do? We say that we have a sum of 5. We say that we have a sum of 5. We take 5. We have 5. I mean, at the first index, remember at the first index we had 5. So if hypothetically, if this I was to be 0, so at the beginning I is equal to 0, so we take the value at 5. Then we'll now see plus. We'll now call this dp recursively, and then at this point in time we don't now put 1. Sorry, we don't now put passing the value of I, or rather the index after I. Remember, we need to skip the index that comes immediately after that I. So we'll now go to what index? We'll go to the index I plus 2. So we go to index I plus 2. So once you go to index I plus 2 and then with the same array, yeah. The other option is we can choose to skip. Yeah, so if we choose to skip, we don't take this 5, then in that case we will now say, okay, you know what, evaluate for me what is the value for dp for the next index, after this is I, after this index, and then with the same array. Yeah, so we can see we have two choices to make for every index. But the important point now is that at the end of the day, we need to return the one that gives us the maximum. Remember, the problem was about what is the maximum sum we can get if we take values from that array without picking adjacent ones. So we need to now see, we need to return back the maximum between whether we chose to take or we chose to skip. So you see the idea now. So this is what we return. This is our solution to this problem. It's just simple. This is the solution to this problem. Whether you choose to do this or not. And then using the approach that we've been using since, we can memorize this. Remember, so we just have like a map somewhere. The key to the map will be the value inside this function that is changing, which is the index. Remember, I is index changing. The array doesn't change, it's the same. Yeah, we could have chosen not to pass in the array into the function actually and have it as a global variable. What changes is this I. So we just have, we can have like a memo somewhere, that says that we just check if their value is in the map. If I is in map, yeah, so then we get that value and then we return it. We get I, return it back. But then if it's not, then we evaluate this. But then before we return this max value, we will set like a value to be equal to this max, and then we memorize it. So we put, we say at the memo, or in this case I'll be calling it map, so let's say map. So we say map dot put. We put in that index I, we put the value inside this value that we calculated, then we return the value. So regarding the time complexity analysis of this, it's the same thing, similar to what we spoke about for Fibonacci. For every evaluation of I, for every DPI call, we are doing 2 DP calls. Yeah, so we are doing 1 and 2, and that is 2 raised to power n. For every point, we are splitting it into two choices at every point. So that's 2, 2 raised to power the n, which is the size of the inputs that we've been given. But with the memorization now, remarkably, when we don't need to evaluate any index multiple times, we want to evaluate it the first time, we just return out the value, and then automatically that now changes to O of n. So from O of 2 raised to the power n, we create a solution that now becomes O of n. This is a lot of improvement regarding time. Imagine that n is, I don't know, maybe imagine that n is 5, you know, if n is 5, this is like 32 computations, and from this one we reduce 32 computations into 5. You can look at the fractional improvements. This is 5 over 32 times 100. Just evaluate it, see the amount of increased time complexity analysis that I've been able to come up with. Yeah, so this is basically the 0 1 knapsack problem. It's a similar idea to the Fibonacci numbers pattern, but at this point, what you need to realize is at every point we have like 2 decisions to make. Sometimes it could be 3 decisions, it could be 4, depending on how the problem comes. But everything, they are all extensions of the 0 1 knapsack. Whether you make a decision, take or not take. Some other times the decision to take or not take might depend on another condition. But I mean, if you can solve problems that relates to this one, with time, the more you solve, the better you get at solving more and more problems that have similar patterns. All right, so thank you guys once again for joining me in another video. I would share some questions that you can use to practice, and hopefully get better in solving these kind of problems. See you guys in another video where we'll be talking about the next dynamic programming pattern on this list, the unbounded knapsack. Please don't forget to like, share, and subscribe. Very important that you subscribe so that you can get notified whenever I drop the next video. Alright guys, see you guys once again. Bye.